So good morning to Dr. and everyone. We are from Group Cluster 2, Team 5. Today we are going to present the problem 3B learning issue, which is the stability of closed loop control system. So the stability can be divided into two processes, which is the unstable process and also the stable process. So the unstable process is the process that been disturbed and it doesn't return to the original value or the set point. Yeah, so this is a graph show that the process is unstable and basically the roots of this system is positive pole. Yeah, so while for the stable process is considered to be a stable if the bounded input is produce a bounded output and regard to the initial step or the set point, and basically is a negative pole of the roots. So this is a graph for the stable process. Yeah. So the next is a general stability criterion. State that the system is stable if all the roots of the characteristic equation are negative or the negative real part. So this is the example of the equation, and now we only consider the set point change only, which we assume this part will be equal to 0, and then the YSP with the set point will bring to the left side to become this equation, which is Y over YSP equal to Km GC GV GP over 1 plus GOL, where the GOL is the GC, GV, GP, and GM. And then the characteristic equation for this transfer function is the denominator of this equation, which is the 1 plus GOL equal to 0. Yeah, and then the roots, the process is stable when the roots determined from the characteristic equation is negative. Otherwise, the process is unstable.
I will move on to the rough stability criterion. First, we need to know the characteristic equations, which is, and for rough stability criterion, we need to convert it to the polynomial form. So there are three tips to analyze the rough stability criterion. First, we need to make sure the polynomial form, the A naught is in positive form. And if it is a negative form, you need to multiply by -1. After the multiplications, if one of the term is negative, that means it is an unstable system and we don't have to do a further analysis. And if all the terms are positive, that means we need to proceed to the rough area. So this is the rough area, and you just need to construct this rough area according to the polynomial. The term all will be formed in the first and second row, and the third and fourth row is the unknown parameter that we need to decide. So how to decide the unknown parameter is that the B1 is minus by the multiplications of this and this over the parameter of an minus 1. The B2 as well is also decided by using an minus 1 multiplied by an minus 4 minus an multiplied by an minus 5 over an minus 1. C1 and C2 will be the same as well. So here is one example of rough stability criterion. The characteristic equation is already in the polynomial form. For your first term, you will be situated in the first column and first row of the rough area. The second term in the first column of second row, and the third term and the fourth term is all situated like that. And the B1, B2, C1 is your unknown parameter that you need to calculate. So the B1 can be decided as what I mentioned earlier on with the equations. So B1 is equal to 17 multiplied by 8 minus 10 multiplied by 1 plus kc over 17. Then the B2 is the 17 multiplied by 0 minus 10 multiplied by 0 over 17. So your final answer is 0. The C1 is the B1 multiplied by 1 plus kc minus 17 multiplied by B2 over B1. So we will get 1 plus kc. So to have a stable system, every element in the left column, in the first column, you need to be make it positive. So in order to obtain the range, you need to make everything to become more than 0. So B1 is 7.41 minus 0.588 kc more than 0. Then you will get the range. And kc plus 1 more than 0, you will get the range. So the final answer is the system will be stable if kc is in the range of -1 and 12.6.
Good morning, everyone. My name is Jasmita. I'm going to present tuning of controllers Cohen-Kuhn technique. First of all, when choosing a tuning strategy for a specific control loop, it is important to match the technique to the control loops and the larger process. Cohen-Kuhn tuning rules work well on virtually all self-regulating processes. And most control loops such as flow rate, temperature, and pressure are at least to some extent self-regulating. And as for us to use Cohen-Kuhn rules, we have to make the process variable and the controller output time trended so that we can take measurements of them. And as you can see, the output and input are drawn in a graph against time so that we can take the measurements of them. In order to do the tuning of Cohen-Kuhn using Cohen-Kuhn technique, we have to place the controller in a manual and wait for the process to settle out. Make a step change of a few percent in the controller output and wait for the process variable to settle out to a new value. And as you can see, this is the graph. There is time delay. Time delay is basically the time difference between the change in controller output and the intersection of tangential line and the original process variable, original level of process variable, which is this. And the slope is the slope of the controller output reaching the inflection point. The inflection point is labeled as B in here. The inflection point and slope is used in calculating the tau. Tau is the time difference between the intersection at the end of that time, which is here, and the process variable reaching 63% of its total change, which is B in this case. And therefore, the tau would be this area, this part of the graph. And for K, which is the constant, we can calculate by B over A, which is output and input over the steady state. And in Cohen-Kuhn technique formula, the formula differs for each controller. For proportional controller, the route stability criterion can be calculated by 1 over K times tau over time delay times 1 plus tau over 3 tau. Time delay over 3 tau. And as for proportional integral controller, PI, the route stability criterion is calculated using this formula, and TI is the integral time interval. TI is calculated using this formula. And as for PID, route to stability criterion is calculated using this formula, and integral time difference is calculated using this formula, and TD is the derivative time interval is calculated using this formula. And as you can see, the technique formula differs from each controller. And that's all from me. Thank you.
I will continue with tuning of controllers Ziegler-Nicholas. This table shows on how to set for each controller. For P controller, Kc equal to 0.5 kcu. For PI controller, Kc is reduced to 0.45 kcu, and for PID controller, the stabilizing effect of derivative actions allow Kc to be increased to 0.6 kcu. For tau I, we only have for controller PI and also PID. For tau D, we only have for controller PID. This table shows how to calculate for Kc, tau I and also tau D for parallel form and also series form. This is the result for determination of the ultimate gain Kcu. For Kc less than Kcu, the closed loop response is usually overdamped. For the ideal case, which is Kc equal to Kcu, continuous cycling occurs. For Kc more than Kcu without saturation, the closed loop system is unstable and will theoretically have an unbounded response. But with saturation, it prevents the response from becoming unbounded and produce continuous cycling. Thank you.